In this video, we'll use factorial and double factorial in the expansion coefficient to generate the Taylor-Maclaurin series sum of hyperbolic cosine. We begin with the dataset of the hyperbolic cosine. So array formula, hyperbolic cosine of the x values from -2 to +2. And we'll chart this. Insert chart, and we'll use scatter chart. Use row 1 as header, column A as label. For the series, show the trend line, polynomial to the 8th degree. And the label, use the equation. For the legend, position at the bottom. Here's the trend line, and trend line polynomial to the 8th degree. We calculate also the Taylor-Maclaurin's series sum expansion of the hyperbolic cosine, which is the summation of a times x to the power 2n, where a comes in two forms. The expansion can be in the factorial form or the double factorial form. And n is from 0 to infinity, so starting from 0 up to infinity. In this case, 16 is good enough. Now we continue with the expansion coefficient using the double factorial. So array formula, 1 over, there are 3 parts. Double factorial 2n minus 1. So factorial double, factorial 2 times n minus 1. That's the first part. The second part, 2 to the power n. So we know that n is from f3 to f19, so we copy that. So times 2 raised to the power n. Finally, the third part, times factorial of n. So factorial of n. Enter. And the factorial form of the expansion series, the expansion coefficient. So array formula, 1 over factorial 2 times n. So we know that n is from f3 to f19. Then enter. You'll notice these values are the same except for the first item. We'll correct this with an if statement. So that is, if n equals 0, then it's 1. Otherwise, calculate. Now these two are the same. Now we can continue completing the Taylor-Maclaurin series sum expansion. This is array formula, series sum of the x values, x to the 2n. So x raised to the power 2n. Now 2n starts from 0. At n equals 0, it's 0. Incremented by 2. 2, 4, 6, 8. And the coefficient will be this range. That's the coefficient. You can also use the a1 or the factorial. I'll show the equation. So edit chart, customize series, trend line, polynomial to the 8th degree. Use the equation as label. And here we have the polynomials are exactly the same. The trend lines are exactly the same. We calculate this polynomial regression coefficient using LINEST. To do that, we complete the LINEST matrix, the LINEST polynomial matrix, starting with the power. That's transpose 0 to 8. Now the elements of the matrix. So this is array formula of the x values raised to the power 0 to 8. Enter. Now we can calculate LINEST, starting with the hyperbolic cosine. So LINEST data y and data x. And the expansion. So LINEST data y and data x. So let's compare the coefficient at x to the 0, 1. Coefficient of x, 0. Coefficient of x squared, zero point 0.5. Coefficient of x cubed, 0. Coefficient of x to the fourth, 0.0417. Coefficient of x to the fifth, 0. Coefficient of x to the sixth, 1.38 times 10 to the minus 3. Coefficient of x to the seventh, 0. Coefficient of x to the eighth, 2.7 times 10 to the minus 5. Suppose we change the expansion coefficient instead of the double factorial. We will use the factorial. So erase this and replace it with the factorial. So we have a different expansion. The datasets are still the same. The trend line hasn't changed. They're still the same. The polynomials are still the same. The coefficients, polynomial regression coefficients, are still the same. This completes the use of factorial and double factorial to generate the Taylor-Maclaurin series sum of hyperbolic cosine and its LINEST polynomial regression.